Hello, welcome to Lattice Developer Conference 2023. Super excited to be with you here today to discuss one of the topics that is often what FPGAs is used for, an imaging pipeline. And specifically, I'm going to focus on low power, small size, consumer application focused ISP and USB connectivities with FPGAs. My name is Hussein Osman. I am a marketing director at Lattice Semiconductor and responsible for some of the consumer applications at Lattice. I've been a user of FPGAs for the last 2 decades. I really enjoy and believe in the power of FPGAs and the capabilities they bring to designers and developers. I have with me today, very excited to have with me, two teams, the Helion team and SLS. I'll let the team members introduce themselves. All right.
Yeah, my name is Arndt Bussmann. I'm the CTO and co-founder of Helion, located in Duisburg. And this year we had 20th anniversary, and therefore we founded as a spin-off of the Fraunhofer Institute here in Duisburg. And since 20 years, we are working in the field of image processing tasks inside FPGAs, especially for ISPs. And yeah, I did my engineering here in Duisburg, and thank you, Hussein, for the possibility here to present our company and solutions.
You're welcome. Thorsten.
Yeah, my name is Thorsten Heimann. I'm also a co-founder of Helion like Arndt, and we met in the past in the Fraunhofer Institute, and we developed there our own image sensor. This is the basis we have to have good knowledge about the ISP, also image signal preprocessing, and to do to get good-looking images for your application.
Thank you. Thank you. All right, Hiral, would you introduce yourself, please?
Thank you, Hussein. My name is Hiral Patadia, and I am working as a senior technical manager at System Layer Solutions since 2009. I am mainly looking after the IP core development and FPGA design and development activities here. And I am engaged with the Lattice and Hussein since many years, and we are enjoying working with Lattice. Thank you, Hussein.
Thank you. Thank you. All right, so today the agenda is we want to talk a little bit about FPGAs in general. What are the use cases? Why are FPGAs used? What are their advantages? Then we'll introduce a camera pipeline and walk through the pieces. And very clearly, there are two big pieces. There's connectivity, and we can talk about all the types of connectivities possible. And one of them is USB and the ISP pipeline. So you get a good overview how to build a USB camera using an FPGA. So FPGAs are used commonly in video applications. They thrive really in high performance video processing. Some of the reasons why FPGAs in terms of architecture are good for video processing is the ability to program the FPGA. FPGAs are completely a blank fabric that come with certain resources like logical tables, DSP, memory, and flexible IOs that surround this fabric. And so these pieces together, they create a programmable chain that can be used to create all types of applications. The parallel compute capabilities of the FPGA provide a way to design performance optimized IP or designs. The ability to have a programmable chip means a reduced time to the market. The designer can make changes throughout the life cycle of the product and push those changes out and delight the user with updates as the product gets used by the user. FPGAs are normally on the shelf for 10 to 15 years. Some of them are for longer when compared with ASICs or other types of silicon devices. You expect 7, 10 years type of a time frame. I touched a little bit on IOs. there's normally a ring of IOs around this programmable fabric of an FPGA, and those IOs assist in bringing data in for processing and taking the data out to the rest of the system. And today we're going to demonstrate how you can use the FPGA IOs to create, for example, USB pipeline. An advantage of parallel compute as well is the ability to create a design that's deterministic in terms of latency. Input to output is always equal to a specific number of cycles, and that tends to be beneficial, especially in applications like video processing. So popular use cases of FPGAs, especially small size FPGAs, is IO bridging. Those flexible IOs can bring in many different protocols and standards into the FPGA, and those can be converted into other interfaces to solve some system level issues with interfacing different sensors or SoCs or devices within a system. Glue logic, normally when you convert protocols or standards or need to move data from one part of the system in certain format to another part of the system with different format, some sort of glue logic is required, and a combination of the IO plus the programmable fabric allows for customized design or state machines to do glue logic. And the third topic here, which is our focus topic for today, is video and AI processing. We'll focus on the video processing part of the popular use cases. If you look at a typical camera within many of the cameras that are deployed today in the world, you're going to find an image sensor. This is an analog to digital converter type of sensor. It connects to the rest of the system through interfaces such as MIPI CSI, a standard interface for connecting cameras. There are blocks for conversion of that data into format that's consumable by the rest of the system. Right after that, you normally see some sort of image signal processing IP that makes the image consumable by the rest of the system, whether it's a user or an AI subsystem down the stream. Normally, there are memory requirements that are associated with this image signal processing block, and that's dependent on the type of processing that needs to be executed on the video stream coming through. And then there are some sort of a host interface. USB, PCIe, Gig Ethernet are some of the popular use cases, and probably those are the three that cover most of the camera types that are out there. And this pipeline then end up with a connection to a host that consumes the video pipeline or the video stream that's coming to the system. So this is a high-level overview of what a pipeline for a camera looks like. And over the next 20 minutes or so, we'll dig deeper into ISP. Helion team will talk to us a little bit about what makes an ISP, what the details of what's inside the ISP, and how to think about performance of an ISP. Before we go into that, FPGAs get used to for ISPs quite a bit, and there are some good reasons for that. So they tend to be lower power than other type of implementation. You're able to do high performance ISPs on a small device. The ability to adjust that ISP pipeline and decide which functions are needed and create a fully flexible pipeline is something that's possible with FPGAs. Might not be so possible with already pre-existing ASIC or SoC that has certain blocks that are coming one after another, and that's how a chain of ISP is constructed for these devices. The flexible IOs allows for selection for many sensors. Basically, a sensor become something that the system designer can choose the type of sensor they're interested in. You can marry AI and detection of let's say a specific scene or object with the intelligence of the ISP to create a more intelligent ISP. The ability to tune for the sensor is something that normally SoC vendors would do, or ASIC vendors. Here you get the full capability with an FPGA normally to tune the ISP the way that the user needs it, or the way that the system would need it for the ability to create a use case via that. With Lattice, you see some devices have very fast boot time, and that drives a capable ISP for a specific application. And then FPGAs tend to have wide temperature range support and ability to go into all types of application, industrial, automotive, or consumer. So with this said, I'll let Helion dig deeper into the ISP piece of it, and we'll come back and talk more about USB. Arndt?
Yeah, thanks again, Hussein. So let us talk a little bit about image sensor processing inside, image signal processing inside FPGAs. And as you know, we are providing such kind of solutions, and our background image here is a bridge, right? The question is why? The reason is we are bridging the gap between the image sensor and the final application, because many processing steps are needed, and all these steps are bundled together into one ISP solution. So next slide, please. Yeah, so Helion and Lattice do have a common history since a lot of years, by the way, much more than 10. It's roughly 15 years, something like this. Our company is 20 years, and we are now working together since 15 years. During this time, we had a lot of joint customer projects. We provided for Lattice guys FAE trainings. We are very deeply integrated into the Lattice technical staff organization, and we are also Red Carpet partner. This makes sure that if we have some, let us say, challenges with some intolerance in the IPs, we have a direct contact to the Lattice guys, and we can solve it very quick for all our customers. And we also partnered several times in order to get evaluation kits out there for HDR60 as an example. It was the first thing we had 12 years ago, and we also partnered up for the EPDK, which is now available on the market. So let's combine. As we can see here, we have several IPs in the market. 20 years ago, we started the development. As you can imagine, we have more than 50 years of work inside this ISP stuff. At the moment, the database has much more than 150 IP cores. And what I can say is we are supporting all Lattice FPGAs since the beginning of the ECP series. So our IP cores are working in Mach-XO as an example, and also in the Wand. So from the very small devices to very large devices, all cores are optimized for all these FPGAs, and therefore we are used as IP library for the Lattice video solutions, and we also did together with Cypress an industrial camera reference design. One unique feature, not all, but one of the unique features is we also have HDR image processing stuff inside. We have several technologies in order to combine multiple exposure stuff or to generate HDR images. We have flexible tone mappers inside. And we have, I think, as one of the single vendors in the market, we have linear image processing in the full pipeline. So we are not converting it or we are not compressing the data stream to something. We are working linear in the full pipeline, and therefore we can provide the full dynamic range, which is developed by the image sensor. Next slide, please. Yeah, in order to get the design working, here you can see the bridge. The bridge is, in this case, this green rectangle. So we are starting in the beginning with the image sensor, of course, and the image sensor does need some setup things, and these setup things are provided by the sensor port. We call it sensor port. And as you can imagine, we have single image sensors in the market from different vendors. Each sensor needs an own setup, and therefore the sensor port is unique for each sensor type. But after this, we are providing internally a data stream which is processed by an universal ISP, we call it. And this ISP is performing all the tasks from the raw data stuff to the final colored image. And then we have here an output interface, and then this output interface can be anything internally or externally in the solution. So therefore, we are providing this ISP either as a standalone solution or as an IP. And we have one unique feature here, and this is nowadays very good possible. It's okay with it. It's the right slide. So no, one slide back, please. Sorry. Yeah. So this is the right one. So what we can do with Lattice FPGAs now, we are able to provide our customers ISP as a companion solution. So what we see in the market is that many customers are using specific SoCs due to reasons they want to use Linux as an example in embedded systems. And all these SoCs don't have either the number cruncher unit inside to process image data, and they don't have the flexibility on the I/Os. And therefore, in front of these SoCs, we are using the ISP as a companion. And then we are using in actual customer projects 7 of the 9 advantages which were presented by Hussein a few slides ago, 7 of them. Because we have a very small package, we have a very cost-effective solutions here. Also, and we are offloading the CPU and DSP stuff. So next slide, please. Yeah, the ISP itself can be delivered in different, let us say, flavors. We are starting with a standard flavor on the left. This is standard called HD ISP. It's capable to process all image data with 1080p60. So it's a standard full HD resolution. And it contains all needed blocks which are needed to get good colored images. Internally, there's also white balancing stuff inside, of course. There's auto exposure stuff inside. We have internal statistics engines. In order to test systems during development, we have test pattern generators inside. And all these features can be accessed with a standard I2C interface, by the way. And we have a configuration interface. Second, we have a so-called enhanced HD ISP. This guy has 16-bit per color. So what does it mean? It's 48-bit per color per pixel, right? And it's much more than which is used on HMI as an example. HMI is using 10 bits for each color. And therefore, we can provide some more advanced functions like lens shading corrections, which are needed to correct faults by the lens itself. We can correct green channel stuff from the image sensor. We can provide several noise correction schemes. We can do image enhancement stuff. And we can also provide here global tone mapper stuff in order to squeeze the high dynamic range of the image sensor to the image at all. But last but not least, we are also providing ISPs for all the AI stuff because the AI networks do need some specific features inside the images. And sometimes these features are not nice for humans, but very nice for these networks. And therefore, we are providing specific ISPs for these solutions. Next slide, please. So this is a full-blown advantage of FPGAs, what you can see here, because we are able to support as many sensor interfaces as you can imagine, starting from the good old-fashioned parallel interface up to MIPC's I2, all the Sony standards like sub-LVDS standards or ECS-LVS, or the high-SPI interface from onsemi, and LVDS interfaces from Sony itself. So from the sensor side, I can say we can support all available interfaces on the market, thanks to the flexibility of the I/Os inside the FPGA. On the output interface side, it's on the right side, the same, right? So we can provide the data as parallel data, as HMI data, DisplayPort, or direct contact to an FX3, or all the MIPI standards also supported like DSI or CSI2. For the imaging, we have, in addition, there are a few more advanced features like overlay stuff, frame buffers, which are used to control the frame rate. We can convert the colors. We can do with external memory, do a 3D noise reduction stuff, and also image stabilization stuff. And from the sensor side, we are supporting all major brands like Sony, OmniVision, onsemi, Aptina, and BAE, and many other guys, but these are the major ones. And on the video formats, yeah, all standards are supported. Next slide, please. So this is, I said it, I think 1 year ago, this is a game changer in the market. It's a Corsair NX17. Why it's a game changer? We have several customer projects which are using exactly this FPGA. And the reason is it's the smallest FPGA of this family, but inside it fits a full-blown ISP of the standard HD resolution. And it's a very small package, it's a very thin package, and it's a very low power solution. And one big advantage is very fast boot time. So all this is inside this Corsair NX, and the pipeline we are using is called then ISP chain, and this ISP chain contains all needed processing blocks, which are configured on the fly, via a register file in the DMA, and it's connected with a memory interface to the RISC-V subsystem, which is provided by Lattice. Next slide, please. So what are the advantages? Yeah, I said it already because I'm very excited about these advantages. One is very small package, of course, low profile package. Very, very important for embedded solutions. And we did for customers large surveys to figure out which FPGAs in the market can be used. And the outcome was Lattice, by the way. So next is, and this is one huge advantage, this is the lowest power consumption we have. We call it quarter watt ISP or Q-watt ISP. Yes, it needs only 0.25 watts for a full-blown ISP with 1080p30. Try to find such a device in the market. So, and we also have the ability to support automotive and industrial-grade devices. We have fastest MIPI I2 stuff, and the guide can also support up to 4K resolution. And this is one of the, I would say, biggest point, we have best support in class. This was the main reason for us 15 years ago to select Lattice for all our solutions. Best support in class. Yeah, next slide, please. Yeah, the full-blown camera, by the way, has then 0.5 watts because the image sensor also needs a little bit current. But the ISP is not the big guy. And this is interesting because competition ISPs do need several watts, by the way. Yeah, the pipeline itself is able to support here on the AVDK 150 megapixels per ISP chain in Corsair NX. This is 1080p60. Or in the one series, the same processing block can provide up to 300 megapixels per second, which is 4K 30. And we can combine all these ISP chains to processing grid for unmatched performance, by the way. Okay, next slide, please. Yeah. Of course, you can buy specific SoCs which do have also ISPs inside, right? But then you have to live with it as it is. And here's a big advantage of the combination of a very good software flow, of an integrated IP library, together with, let us say, smart IPs. What is smart here? Smart is we have one block, it's called ISP chain, and during the design phase, the customer can select which kind of blocks the customer wants to use inside the ISP chain. And therefore, the customer has direct influence on the footprint, which is consumed by the ISP core itself. And this is done during the design phase, but also we have a configuration interface. And with the given blocks which are used inside the design, these blocks can then be configured on the fly in the FPGA itself. Next slide, please. Yeah, you can see here, this is one of the demo stuff. So if you did everything okay, then you will see something like this, right? So this is the output image to check if the FPGA is working, is the ISP chain itself working, is the clocking working, and so on. So thank you. You will find us here in Duisburg, located in the western part of Germany. On the right side, you can see our building. So we are located in the second floor, yes, right. And it's the southern part of Duisburg. Very nice city. And by the way, you wouldn't believe it, but this guy here in the background is only, let us say, 10 kilometers away to us, so yeah, something like that.
Yeah,
so,
yeah. Indeed.
You're welcome for new projects. Again, thank you so much, Hussein, for the presentation.
Thank you.
Hussein,
we don't hear you.
Okay. Hopefully you hear me now. So thank you, Arnd. Great overview of ISP processing and the different types of blocks, sensors, different IPs that Helion provides, and advantages of running those on an FPGA. So the data comes in from a sensor, gets processed, the data needs to go to a host. One of the most popular interfaces to data between cameras and host is USB, and Lattice and SLS has been working for a number of years to ensure a product portfolio that allows for different speeds of ISP host versus device configurations. And Hiral will walk us through some of that offering from SLS. Hiral, let me know if you want me to go next slide here.
Sure. Thanks, Hussein. Basically, SLS was established in 2002, and since then we are providing turnkey technology solutions globally. We are providing IP core and FPGA design development, product design, prototype design, software development, and manufacturing facilities as well. In this presentation, I'll walk you through the IP core and FPGA design capabilities, as well as the different USB IP core portfolios we have. So next slide, please. So let's start with the design capabilities that we have gained over the years so far. So we are a very proud member of Lattice Partner Network. We are working with Lattice since many years. We have good success stories with different customers as well. We do have our own IP cores. We also customize the IP cores for a specific use case. We provide FPGA turnkey solutions that includes the board designs, software development, everything. We do have worked on ASIC to FPGA conversions, because some of our customers came with us saying that this ASIC that is not available or at end of life from the vendor, and we need the same functionality without modifying any software at the host side. So we also do some ASIC to FPGA solutions as well. We do driver developments for all of our IP cores as well as the customers' requirement. And we are serving our different customers for 20 plus years, and we have a good number of success stories. Next slide, please. So now let's let's go through about for the USB IP core portfolios that we have in our cart. SLS started working on USB technologies in 2004, and we released our first USB IP core in around 2006. And since then, we have been adding more and more IP cores, USB IP cores in our portfolios. So now we have, starting from USB 1.1, we have USB 2.0, and we also have these next generation USB 3 IP cores as well. And not only the IP cores, we also have the device functionality, host functionality, hub functionality, OTG, everything in our USB portfolio. Next slide, please. So SLS not provide the IP cores only. We also provide supporting software, supporting firmware applications in source form, so that the customer can reduce that development time. And these all IP cores and firmware software are validated on all the Lattice FPGAs, so we can say it's ready to use solutions for the user. Next slide, please. So these are a high-level overview of our USB 2 host/device controller, because it has both the functionality. This IP core supports high-speed, full-speed modes. High speed is about 480 Mbps, and full speed is of 12 Mbps link speed. For high-speed mode, which is 480 Mbps, this needs the external ULPI PHY. But in case of full speed mode, we have designed inbuilt five configurabilities so that there is no any external ULPI 5 is required. This IP core is, since we targeted this IP core for FPGA, we have make this IP core fully parameterized. So you can use it as per your requirement. You can use it as a standalone host controller, standalone device controller, or with a combined functionality of host and device controller. We are, the IP core is compliant, fully compliant with the USB 2.0 specifications, and the IP core is also ASIC proven. Next slide, please. So this is one of our latest IP core, which is a USB 3 device controller. This supports the 5 gigabits per second of link speed, and the good thing is it also doesn't require any external PHY for USB 3 functionality. We are using Lattice FPGAs on chip transceiver, 5 gig transceiver, to get the functionality of USB 3 PHY. So this IP core is fully backward compatible with the USB 1.1, USB 2.0, and USB 3 as well. For, as mentioned, for USB 2 high-speed mode, this requires external ULPI 5. However, for USB 1.1, which is 12 Mbps, this doesn't require any external PHY. So it's very easy to use the IP core in any of the design. We are supporting up to 31 endpoints, 15 in endpoints, 15 out endpoints, and all type of transfer modes are supported here. That includes bulk transfer, interrupt transfer, periodic, or the isochronous transfer. And all the endpoints are configurable. You can change, you can optimize the resource usage as per your requirement, and the maximum speed performance we have achieved is around 3.5 gigabits per second, which is with the raw read-write operation. Next slide, please. So this is one of our hardware capabilities. We have designed FMC daughter card that sits on the Lattice Crosslink NX evaluation board. This FMC daughter card provides the USB 3 interface to validate the IP core functionalities. So user can have this Lattice evaluation kit as well as FMC daughter card, and they can design any kind of prototype for their evaluation, for the evaluation. Next slide, please. So in the beginning, like Hussein mentioned, there are some many use cases which requires or which is very useful for USB applications. So this is one of the use case that is a IO aggregation, or we can say some low speed peripheral control over the USB. So we have a ready to use solution for two types of with two types of architecture. The upper architecture is using a soft processor, which is a RISC-V processor, to process all the request and to encode decode all types of packets, whether it's I2C, whether it's a SPI, or it's a GPIO. The bottom architecture is a standalone USB device controller, and that doesn't require any type of soft processor to encode, decode, or process any request. And another good thing about this solution is we are not using any custom drivers at the Windows side. We are using the inbuilt drivers which is available in Windows 11 or Windows 10. So that makes the task very easy and compatible with a broad appliances. Next slide, please. This is another use case for the video applications or imaging applications. This we have designed this prototype for our different customers. So this basically gets camera data, camera input from the MIPI sensors. You can connect up to 2 sensors, and as of now, there is no ISP involved in this prototype. We are aggregating the both camera data and sending it via the USB SLS USB 3 device controller to the Windows applications. And again, in this as well, we are not using any of the custom drivers. We are following USB video class, which is defined by the USB organization, and any operating system, including Linux or Windows, has the built-in drivers for the all type of USB devices. Since we can achieve up to 3.5 gigabits per second of throughput, we can run the full HD uncompressed camera with the 60 up to 60 FPS. Next slide, please. So those are the some use cases that SLS has designed, and these are some more use cases that can be where the USB IP cores can be utilized. That includes the medical appliances, automotive test measurements, some of the defense and data storage, data acquisition. We have done all types of project in different fields, and we do have many ready-to-use reference design for all types of markets. Next slide, please. So these again some more detailed use cases. So like we discussed, it's a high resolution camera development. We can also use this for high speed ADC data capture for any lab analysis or any high speed data analysis. It is widely used for factory automations. Many of our customers are using our IP cores to validate the either host or device functionality of their product during a mass production at the factory. And many of our customers are now working to upgrade their older systems which doesn't has the USB, or working with some kind of PCIe or gigabit Ethernet, and they are now working to upgrade their system using a USB. There are many video converters as well available that converts SDI to USB or other any data format to the USB. And of course, hard drives are evergreen for the USB applications. Next slide, please. All right, so that's it. Thank you, Hussain.
Okay, so just to summarize our discussion today, we talked a little bit about FPGAs and why FPGAs are used for video processing. Some of those things are the reasons or advantages is the flexible IOs, the programmable fabric, and we also talked about some of the common USB designs that SLS provides and the ISP pipeline Helion has put together and provided for us. And all of those come together on an FPGA to create a ISP pipeline that's fully customizable, flexible, high performance at a power envelope that's lower than existing SoC-based ISPs. So with this, would like to transition into Q&A. So if you didn't notice, there's a Q&A button that you can press on and provide some questions. I've already got a few questions here, so we'll walk through those, and feel free to add additional questions as we discuss those. So the first question, and this is to Hiral, is SLS IP core available for evaluation?
Yes, we do provide evaluation license to our users to evaluate the IP core, and they can extend the evaluation period till they are satisfied for the functionality.
So this IP core comes as a black box with clear definition for how to get data in and what to expect at the output of the IP.
Correct. So IP package includes reference design, different documents, tutorials, the embedded codes, the host applications, everything.
So that's another question, is the reference design for MIPI, camera, ISP, USB 3 available?
So as of now, it's not available, but we are working to integrate ISP, and then we'll have the full reference design available for the users.
Yeah, I think that's a really good goal for us all, 3 companies. We can put together these reference design. Right now, we enable the development of this entire pipeline, but I don't think we've put out an entire reference design for the pipeline. So in the next 3 months, 6 months, that would be a good target for us to put together an entire pipeline. Okay, this is question for Helion. How does implementing the ISP and FPGA improve the overall system compared to solution without FPGA and processing ISP in DSP, especially in terms of efficiency?
Yeah, of course, you can buy such kind of SoC, but then you have to live with it as it is, right? And the FPGA has several advantages, like we have low power consumption, we have the ability to support several sensors at the same time, or we can support different kind of IOs. This is very easy to handle. And if during the project it turns out that you need an additional processing block, then you can easily insert it inside the FPGA, but there's no way to add it inside an SoC.
Okay, thank you, Aaron. Next question, again, for Helion. Is it complicated to configure or adjust the ISP? Do I need to have a deep knowledge of the FPGA programming?
Yeah, that's the good news. No, because we are all FPGAs guys, and we like to work with FPGAs and software tool stuff. But our design goal was to make access to ISP features very easy to handle, to enable customers just to set up the feature set. And therefore, we have a kind of memory interface, and the customer can edit the memory file, just entry its ASCII text, right? And you can just insert the default parameter settings. And then these settings are used inside the ISP. And it's also inside a memory map, inside the RISC-V CPU available. And then typical embedded programmer guys with C knowledge can set up the ISP. So there's no special FPGA knowledge needed in order to use this ISP.
And also one thing I want to add is that also during runtime, you can access the ISP, for instance, during I2C or something like that. So another processor can control the ISP, and it's not necessary to do special algorithms inside the FPGA. It could also be external and controlled via I2C.
Okay, thank you. So, Thorsten and Arne, a lot of times I see customers looking or want to tune their specific ISP the way they want it to look. It feels like it's an art. It's something that everybody has a different feel for.
Yeah.
Does your ISP allow for a customer to come in and tune the ISP? I think that would be an advantage to having such a flexible pipeline, is the ability to tune it in a specific way. Is that possible?
Yeah, this is possible. Of course, you said it's kind of artist thing. The good news is no, because everybody of us can judge, is it a nice image or not, right? It's very easy, but the trick is to figure out the right parameters for it. And therefore, we are also, if needed, trainings for customers in order to know the KPIs of the system, to know how to set up specific setups in order to get specific numbers which are used for the tuning itself. Of course, you can do tuning just by playing, just adjusting parameters to see what is it. But if you want to have a kind of, let us say, color correction stuff or so, or lens shading correction, then you need, of course, the right setup in order to do this. And we are providing such kind of setups, and other companies too, that customers are enabled to do their own image tuning on the ISP.
Okay, sounds good. So here I have a couple of questions. Question number one of the use cases you've shown was aggregation of interfaces. I think it was SPI and I2C or GPIOs, this type of interfaces. So the question is, they exist devices off the shelf that can do this function. Why should this be done on an FPGA? What advantage do you get from doing this on an FPGA?
So first is the this is a low power solution. So you will have for all the portable devices, you will have to save powers. So this will help you a lot to save powers. You can readily use this solution, so you don't need any programming programming capabilities, or you don't need to learn any coding for this. You just take off the shelf solution and put it in your product. So I guess these are the two biggest advantages, and yes, the price is as well. So I guess these are the biggest advantages of using the FPGA.
Yeah, and I think, the number of interfaces inputted and what type of interfaces. So the off the shelf, you might get two I2Cs, two SPIs. Here, if you want more interfaces all over single interface over USB, you get to choose and program those, and they're not hard to specific functions.
Right.
Multiple times the question is around ULPI PHY is required for USB 2. It seems like USB full speed, you use FPGA IOs, super speed, you use FPGA IOs. Why is it required to have a ULPI PHY?
Right. So technically, for the USB 2.0, the differential line specification is a bit different. It's not pure differential line, and it's not pure single-ended line. It has to work in both mode. In the beginning, it has to work as a single-ended lines, while when it switches to the high-speed mode, it has to work as a true differential line. And this is something, this type of IOs are not available with any of the FPGAs. That is, those are available in the market. And this is the only reason this requires an external ULPI PHY. So it's mainly the IO capability constraint, nothing else.
Okay, understood. I want to thank you for your time. This has been a great session, learning experience for me. We hope the viewers also have an educational session. If we didn't get to your questions, we will get a list of questions offline, and we'll get back to you with some answers here. Really appreciate your time, and happy to work with SLS and Helion to bring together ISP and connectivity interfaces solution on Lattice FPGAs. Thank you.
Thank you.
You're welcome. Thank you.
Bye-bye.
Thank you too.